Welcome to today's webinar, an introduction to heat pumps and solar thermal. This is part of a webinar series brought to you by the Local London Green Jobs and Skills Partnership. The aim of this webinar series is to support your learning and open up the world of green and digital opportunities in the property and construction sector and beyond. At the end of the webinar, we'll ask you to complete a short quiz using a QR code, which your tutors will give to you. I will now hand over to Richard Love at Quantum Group. I think he's beamed in from Raynham, and he's an experienced professional, and he'll be able to take you through the webinar for today. Now over to Richard. Get ready with your questions, and I hope you enjoy the webinar.
Brilliant. Thank you very much. Right, yes, my name is Richard Love. I'm working with the Quantum Group, and we're providing training and resources for colleges right the way across London at the moment, and we're hoping to broaden that out. We've also written some sustainable energy courses and some resource material to go with that. So some of your colleges will already have our installations in them, and you will be encountering some of our courses as you go along. So today's topic, we're looking at solar thermal and heat pumps. I'd like to set the scene, really. I'm part of a generation of plumbers who we were brought up on gas. So essentially, the only option that you had for your house was either going to be gas or oil, and that's the trade that we grew up in. So we spent a lot of time working on appliances, which were not terribly efficient from the efficiency point of view, maybe 45%, maybe 50%, some of those old gas boilers. And it wasn't really considered to be an issue. It wasn't a subject that we were taking a lot of interest in, to be honest. We were more interested in doing away with the coal fires, bringing in gas, getting that equipment to work. And so that was really our focus, was saying that we want to warm the house. We were interested in getting the systems to work. And those boilers were pretty basic, very few electric controls, just really a lump of cast iron with a flame underneath it. So not very technological. And we didn't think about emissions at all. So just one of those situations where society hadn't really recognised what was going on. So from there, I've been doing that since way before most of you were born. And then moved into teaching. And it becomes pretty obvious once you start teaching that you've got quite a broad range of things to look at when you start to teach a subject. I remember when the Kyoto summit first happened, governments was probably one of the first times that governments got together and said we need to start thinking about emissions. What had started to happen is the world authorities, the people who are monitoring these things, had started to notice that there were changes in the climate. And at first it was put down to just a change, not really anything to worry about. But as the science went on, we started to notice more and more changes, and those changes were happening more quickly. So why am I mentioning that to a group of plumbers? Well, hi to the ones that have just joined. Hello. My name is Richard Love. I've just started to set the scene as to why we are interested in moving into heat pumps and solar thermal, and why we're looking at these renewable energy appliances now. So emissions weren't really thought of as much of a problem. We didn't really know the effects of that. But as I say, as the science got bigger, world governments started to think in terms of what are we actually putting out into the planet. So what starts to happen is that all of those trade courses start to have environmental units. They start to have an awareness of the different things that are going on. So it started to come into us in the trades as little courses that were tacked in. We'd be doing the plumbing course or the electrical course, and we would start to have these little units which the awarding bodies were coming up with. We were looking at those and going, oh, that's interesting. Why are we teaching this? And it picks up on something which is pretty basic to all of our trades, that actually the people doing the designing, 9 times out of 10 are you. So you're working as a plumber, you're working as an electrician, you're the one that's going into that property and saying, customer doesn't know, they're asking you, what should I fit? What options have I got? What sort of decisions do I make? And so we realized as an industry that we needed to be aware of much broader than simply our plumbing, but more about the design and the repercussions of those designs. And so we found that as tutors, we were getting asked to teach more and more of this, which meant that we started getting more interested. I started looking into renewable energy back in the 2000s, and the manufacturers immediately responded as well. So what difference does it make whether your engineers know about energy efficiency? The damage that's being done, we've picked up on quite a bit of the research. The damage that's being done globally by the emissions, so essentially it's CO2 that's causing us our biggest problem. So the CO2, as part of that combustion process, once we burn the hydrogen, so we've got CO2 left. That CO2 is going into the atmosphere and affecting the nature of the atmosphere. So that's our first problem. One of those issues then that we want to start to address is, how do we reduce our CO2 emissions? Our CO2 emissions, where do they come from? From transport, from the heating of properties, from our commercial activity. These are all generators of CO2. So what sort of decisions could we make as engineers that would make a difference to that, and how much responsibility, what point do we become responsible and start to think, well, actually the decisions we make can make a difference. The things that we install can make a difference, and start to have a more general awareness of our activities and what they're doing to those from those issues. So where did we start? The industry then started to look at our activities. So what are our activities that are making a difference here? What are the installs that are making a difference? And it started around about the year 2000. The government started to say, we're still going to carry on fitting gas boilers, but they now have to be A-rated appliances. So we started hearing about energy efficiency. We could only fit boilers that were within a certain band. They had to be efficient boilers. And in plumbing terms, that became, we could only fit condensing boilers. And that uses the latent heat principle, so we could extract more heat energy from that appliance. So we started fitting those energy efficient boilers. The electrical industry started looking at electric boilers. Some of those being developed. And so they became viable options and were marketed, all of which we're looking to do, reduce the CO2. The more efficient the boiler is, the less CO2 it puts out. If you can go for electric heating, any form of electric heating is going to produce no emissions except at the source. So from an industry point of view, from a trade point of view, we started looking to make decisions which were going to save energy and basically try and do our bit to alleviate some of the problems caused by this CO2 production. One of the arguments you're going to hear, and one of the comments you're going to hear quite a lot, is what difference does it make if I do it? What difference does it make? How much difference is me making these decisions going to make? And it's one of those things where there's a couple of different answers to that. The first one is, you are an example. You're designing for the people you're designing for. You're an example to the people that you work with. But also, more importantly, your little bit that you do, if everybody does their own little bit, we may not be able to reverse the damage that we've done, but we can definitely reduce the harm by taking these measures now. So the reason that I'm talking to you, the reason that your training courses have started putting this in, because you are the engineers of the future. So decisions that you make and the way you make those decisions is going to affect the emissions from this country. Every time one of you fits a heat pump rather than a gas boiler, you have just reduced the emissions that Britain's going to put out. So so from that point of view, this sort of intro part says, why are we having these thoughts? Why are we having these thoughts? So can we take a pause for a moment and see if we just take a pause and say, have I laid out for you the case of what we're doing today? Does somebody want to make a comment, or does somebody want to say something to me, or put it in the chat? Do you sort of get where I'm coming from? Has that come across?
If there's any questions, you can put them in the chat and then I can ask them.
Got some thumbs up. That's an encouraging sign. And plus it means you can hear me.
Anyone?
No, I think mine have gone a little bit shy.
They're a bit shy, yeah, no, I get that. If there's anything you want to pass on to any of your sort of lecturers, then we can, you know, and then we can just sort of, you type it into the chat on the top toolbar, and then we can ask anything you want if there's if anyone's feeling they don't want to speak out, no problem. Okay.
Good. Okay. Well, let me carry on from here then. So here I am, you know, worked as a crusty old gas engineer for all this time, and start to look at this new stuff and say, well, why, you know, what's the big difference? The biggest single difference is that we've been stuck in a bit of a rut and said that the gas supply, we got it free from the North Sea. It was a bit of a no-brainer. We've got this free energy. We're going to use it. That was fine. That was the number one option. It was cheap. It's efficient, and that was that. The electrical side was always slightly dearer. Electric boilers dearer to run, and so we were at a bit of a point of equilibrium, if you like. There was no great driver for us to change. That started to shift when the manufacturers started to go down the road of producing these heat pumps. And so the next section that I want to pick on really is to start looking at why a heat pump rather than a gas boiler. Have we got any questions from the chat?
Sorry, we have. Sorry to pause you. Cool. So Alan has asked from NCC, I believe, Alan, how much carbon do you think a heat pump will produce compared to a condensing boiler?
We've got the actual figures in our course that we wrote. It's very dramatic. There is no carbon production from the heat pump itself. So as that heat pump runs, I'll qualify the answer, but at the moment, as that heat pump runs, there is no carbon production at all. So your combination boiler will be putting out, I think it's something like 0.98 in your heat pump would be something like generating 0.4 kilograms per year. That's just off the top of my head, but it is that radically different. So the gas boiler, all of those emissions, the combustion process puts out those emissions all the time. The heat pump basically doesn't put out any emissions. However, we are forced, when we think about the calculations, to remember it doesn't help if we're burning gas to generate the electricity, then that has to be taken into account. So really one of the drives, we're coming at this from a couple of different directions. What we're saying is we want to remove the CO2 from the point of delivery, which is great. We get rid of the gas boiler. The air source heat pump goes in, no emissions whatsoever. However, that electricity that it's using has generated some emissions. So the more renewable energy, and this comes out in the course that we've done to go into phase. What starts to happen is the drive for wind farms. They're constantly increasing, and I think we're up into near the 20%. We're certainly on par with Europe and America with the amount of renewable energy that we're generating now through wind farms, solar. And it's a little bit of a Wild West situation at the moment. Every idea is a good idea, and generating it's losing the carbon generation at the point of generation now is our next big challenge. But totally different. So from the point of view of the actual appliance itself, we get nothing. There is no combustion inside an air source heat pump. Did you have any other questions?
That's one. I think that's all for now.
That's all,
Oh, hold
cool.
on. So hold on. So as renewable generation goes up,
Yeah.
the less carbon will be used.
Yeah, absolutely.
To
And that's-
summarise.
And that's really our target. So these two go hand in hand. None of these things happen until government gets interested and is starting to subsidise, and it becomes a more general discussion. And that has now happened. It's been a bit slow, but that was for a lot of reasons. But government now is totally behind it. They are funding a lot of research projects, and they are 100% supporting us as an industry. Anyone fitting a heat pump at the moment will get £7,500 grant. If they're taking a gas boiler out and putting a heat pump in, they will get a £7.5 grand grant to help them do that, to go towards the costs. So I'm quite critical of the government quite often, but with things like that, you know, that's great. That's what we need. If you want a new product to be taken up, and then when people have them fitted and they work, and other people, you know, we need then that to be gossiped where other people are saying, I've got one, it's great. And then it'll snowball. But what they've done is given that impetus by putting the money in. And they're also researching loads of forms of other renewable energy sources other than wind. Wind is great, but obviously there are days when the wind doesn't blow. And so that's happening as well. So the actual heat pump itself, let's start to talk about what it does. Essentially, the reason that the electric boiler was always dearer than the gas boiler, our traditional electric boilers were a heater element that was heating up water. It's a resistance, so as the current passes through, the resistance generates the heat. That will generate. So you buy a kilowatt of energy, you get a kilowatt of heat. With the gas boiler, you buy a kilowatt of energy, so your gas, you buy enough cubic meterage of gas. 1 cubic meter's got about 12.5 kilowatts in it. So you buy a kilowatt of electricity, buy a kilowatt of gas. Your appliance will put 90% of that heat into the water, which is a fantastic achievement. So 0.9 of a kilowatt of heat energy will go into the water. The electric boiler, again, way up there, it'll be in the high 90s% efficiency. So you buy a kilowatt, you get just under a kilowatt. We're going to look at the way a heat pump works in a minute, because what a heat pump does is uses the refrigeration cycle, and it uses the refrigeration cycle, which I'll explain to you in a minute. It essentially, you buy 1 kilowatt of electricity, you run the pumps and the compressor, and you get 3, possibly 4 kilowatts of usable heat into your water. So this appliance is 300 to 400% efficient. So this is where the big drive to fit them comes. We literally I'm going to run that through for you. Again, you buy a kilowatt of gas, you get 0.9 of a kilowatt in your water. You buy a heat pump, you run that heat pump, 1 kilowatt of electricity gives you 3 or 4, ranges in between, kilowatts of usable heat. So it's a bit of a no-brainer from the energy efficiency point of view. There is now an appliance which will give you more heat energy than you actually bought. So that 3-to-1 ratio, fantastic. And that's why they're being pushed. The reason that we're embracing them and saying this is definitely the way to go for the future is that we end up with an efficient appliance. And if you take that to its logical conclusion and say, well, look, if we've got a wind-powered generation of electricity, that electricity then runs through, so we've got 0 carbon when we generate the electricity. We run that through to a heat pump, and we have 0 carbon emissions when that heat pump runs. And every time we get 1 kilowatt from our wind farm, that becomes 3 kilowatts of heat. You start to see why we're going that way as an industry. It takes so much carbon out of the process. You end up with 3 times more heat than you actually bought, and just the whole thing. And that's now. So as usual at the beginning of these things, you know, the first boilers that I started fitting were great big lumpy things and big lumps of cast iron. And over the years, they became more and more and more refined. So the heat pump we've got, the heat pump I'm sitting on, and you're going to have in your bay, by the time you're well into your careers, they'll be smaller, they'll be more efficient, there'll be more power out of them. So at the moment, this is it. It's a big fan, essentially. We have a big fan unit. It's drawn in, the air is from the back and expelled out the front. And then basically the pump and compressor sit next to it. So it's an external unit. The idea is that you will put it somewhere, you can put it somewhere out of the way. They're very quiet in operation. And the rules we're looking for, 65 decibels, nothing above 65 decibels. So the actual process, let's have a little look at the actual process then. So what we do, we draw air in through the unit. We run it through a compression process so that air is compressed. Once you compress, you release heat. When it expands again, it draws heat in. And we've got some slides. I want to take you through that process step by step. So we've got some slides, which I want to take you through the components actually inside the unit. So we've got sketches here of them to try and make it clear for you. And I want to just take you through this because it's the basic way that the whole thing works. So I'm hoping you can see that. Timetable.
Nope. Can you see the blue, everyone?
Yeah. Can you see the screen?
No, I think it turned it off. It was on earlier.
Hold on one sec.
Yeah, that's it.
Is that it? Okay.
Lovely. Okay. So I'm going to take you through this. Follow it through with me. So we have a fluid refrigerant, which we're going to run through a cycle. We're going to use it. We're going to take it through an evaporator. It's a closed loop. We're going to run it through a compressor, and then we're going to run it through a condenser, and then we're going to, at the end, expand it again. So this refrigerant, this liquid, we're going to run it through one side of the process where it will be a liquid, and then we're going to run it through the other side of the process where it will be a gas. So what's coming up on the screen now is the first, we just flick through them. So our refrigerant fluids are capable of absorbing heat and releasing it. That's the key for us. So take us through to the next slide, please. So this is the first part of the process. This is the big fan that the air from outside is drawn in. So this is the low pressure side. The refrigerant is a gas, and what will happen is these slides will build on each other, and eventually at the end of it, we'll have a picture of the whole circle. So this is a circuit that's contained within the heat pump. It runs through to the outside. Air from the outside is drawn in. Heat energy from that hot air is absorbed as part of that process. So we've taken heat energy from the air outside. Now we run it through a compressor. So what we've done, we've had low heat energy at low pressure, and now we squeeze it through a compressor and it will turn it into high heat energy. So we just picked up on that before we move on. The air from outside, and this will carry on working right the way down to -15, -20. We take heat energy from the air outside. The air on one side of that fan will be 5 degrees lower, roughly 5 degrees lower than the other side. So we're going to pull in about 5 degrees of heat out of the air. We're going to put it into that gas, and then we're going to move it around the system. So the next thing we're going to do is compress it. So once we've compressed it, the temperature will go up. Just slip through there. I'm guessing we don't want to go through the actual volume calculations today. Something tells me. So here we have it starting to build together. So we're pulling the air in from outside, running it through the compressor. So go through the next one. So we're running it through, we're squeezing it and turning it into the red dots indicate your high temperature. So we're low temperature, low pressure. We squeeze it, and now it goes through onto the liquid side. So it will now be turned to liquid, and we will now have high temperature that we can absorb and put into our house. it will carry on round the cycle. Yep, do the next one. Yep, there we go. So let's just take this through again. We've pulled air in from outside. At low temperature, we've pulled in some low temperature heat energy, which we've gained just by hotter to cooler, heat travelling from the hotter to the cooler. So that blue side has picked up low temperature. It's a low pressure side, it's picked up low temperature. We've squeezed it, so it will release high temperature because it's at high pressure. It will have turned into a liquid. We're using that change of state where we can change from a liquid to a gas and then from a gas back to a liquid. So in the blue section, it's a gas. When it goes through to the red section, it's a liquid. So we pass it through the compressor. It's then high temperature, which we can take off into our house. We're then going to let it expand again, so it'll change from a liquid back to a gas. We go to the next one, put the whole thing together, and there you have the whole cycle. So let me just run through that cycle for you. The blue section, that's the fan unit on the outside of the building. You've got a fan unit, it's pulling in air, so it's pulling in heat energy. It's then running through a compressor. It's then turning that into high heat energy. So we've gone from low heat energy in a gas to high heat energy in a liquid, taking it around the rest of the cycle. So we've absorbed some heat to take into our house, take it through the rest of the cycle, evaporate it again back into a gas where it can pick some more heat up, take it round and carry on around that cycle. So it is picking up heat from outside at low temperature, and then it's dumping that heat into our house at high temperature. So you can see there is no combustion here. That refrigerant gas just goes round and round in the same loop, absorbing heat on one side, releasing the heat on the other. And that way, we're literally taking heat from outside of our house, picking it up and pushing it into our house. No carbon production whatsoever. So that whole process will sit there churning away. And that's fine if you can come out the slides. And
Everyone gone. Hold on.
we're just going to have to work out how to get rid of the slides.
Hold on.
Are we back?
There we go. We're back.
Yeah, we're back. Right.
Sharing.
The chances of me not leaving you behind are pretty remote. Have we got some questions? Did that make sense? Did that, in a general terms, does that make sense?
Yeah, in the way I explained it, so you explained it quite well. It's essentially it's a freezer, isn't it? Reverse. So if you feel the back of the freezer, it's warm, and the heat is sucking out. Even though you don't put anything warm in the freezer runs colder. Therefore, heat transfer hot and cold. It sucks out the heat from the cold chicken you put in or something like that.
Yeah, that's exactly it. So the technology itself isn't new. You know, we've had fridges since the 30s. So those fridges or those freezers have been around since the 30s, probably slightly earlier than that. And so what we've done is taken that idea and we've got the materials now, we've got the electronics now, and turned that into a usable domestic appliance. Literally taking heat from one place and putting it to another. So the big thing for us is this total lack of carbon production. We're not producing any carbon. Right.
There's one more question here. It's why do they cost so much when the technology is basically that from a fridge? These are quite cheap and old technology. Also, do you think there could be a future environmental issue when the refrigerant leaks out?
Yes. Yes. So the first one is the cost. We're very closely linked to Daikin, who are one of the major manufacturers, and I've asked that question on several occasions because I also do some install work and I work with other companies that do install work. So the reason for the cost at the moment is everybody's getting their research and development money back. I think that's probably the basic answer. But more importantly, it's economies of scale. So when you consider that, you know, they were talking about a couple of years of gas boilers going in for another 4 years on new builds, and that will be round about 4 million boilers. So when you consider those sort of numbers, at the moment, the manufacturers are geared up for mass production and have got mass sales. And it's only really when you can hit those mass sales that the price will start coming down. So it's a bit of a two-pronged thing. The first one is it is early days, and so there's a lot of research and development still going on, and the companies want to recoup some of that. They will always try and factor that in the early days. You know, the first mobile phones were like £2,000, and the first video recorders were, you know, hundreds and hundreds of pounds. And so it's not until it becomes a mainstream thing. So although there's a lot being fitted, the manufacturers are nowhere near yet where they can start to reduce the costs. So that's the first thing. So yeah, that's why they're so expensive. You've still got research and development money, and they're just not making the numbers yet. Daikin, the manufacturer we know about, they've just opened a new factory, and so you know they've built a new factory. It's very automated. Once that kicks in and once they start producing, it's all going to be around sales. Once the sales really pick up, then you're going to see those prices coming down, because then you'll get the competition in the market. If I can buy a Hitachi one for, you know, £1,000 cheaper, I'm going to go with Hitachi. No one's got brand loyalty yet, unless it's a gas boiler. A lot of the boiler manufacturers had enough sense to start manufacturing them as well straight away. From the environmental point of view, the refrigerant gases are always a problem. The original refrigerant gases, which were the CFCs that were talked about a lot, they did a lot of environmental damage. The new ones are much more benign, but yes, there is a qualification called an F-gas qualification, and you will find that the disposal of those gases is very closely monitored at the moment. There's a lot of regulations about it, and you can't just scrap. It's the same with fridges. You can't just scrap a fridge. It has to be, you know, it has to be taken to a site where it's actually going to be decommissioned and the gases will be taken out. Yeah, there is an environmental issue with that. Yes, definitely. But the sort of the systems are in place for that to be dealt with properly, and responsible firms will do that. Of course, we're always vulnerable to irresponsible firms. Yeah.
There's another question about that you mentioned about the £7,000 grant. How much would it cost to replace a boiler with a heat pump? Would the flow and return temps be lower? If so, how much bigger on average would I have to make my radiators?
Yes, this is why, this is one of the reasons we're into so much money. So at the moment we have our radiator systems will have been installed for that 75 degree flow and return. So our delta T calculations, our temperature difference calculations are radically different. There are a lot of manufacturers talking about different outputs, but in reality, your average heat pump, if you average it out, won't have more than 55 degrees coming out of it unless it has an electric heater that tops it up. So one of our big issues from an install point of view is that to start with, if you're replacing a combi, you're going to have to put a cylinder in. Secondly, that cylinder has to be set for heat pumps, because heat pumps have a few requirements that boilers don't have. There is a minimum flow rate that your heat pump will work on, and it's considerably worse than your gas boiler. So the heat pump itself has to have a minimum flow rate. So system design is slightly different. We do central heating priority with the volumizer rather than hot water priority. So those design changes. And the biggest single one is the radiator. All of the manufacturers now, when you look at a rad list now, they will give you two different delta T's. They'll give you a 55 and a 30 temperature difference. And you can see that's quite a radical difference. If you look at the output of that radiator will put out significantly less. One of our nice little ways around it that we're doing at the moment is essentially we're just doubling up. If it's a single panel, we'll get a double panel the same size and put that in. But yeah, we're talking about maybe a third again on that rad size, and you'll hear different things from different people, but one of our main problems is the systems aren't designed. Now, those regs have now changed. So any new gas boiler installation has to be set to run at 55 degrees. It has to be sized to run at 55 degrees on the primaries, and that will accommodate that in the future. So it would mean if you had a modern system and decided to upgrade to a heat pump when that boiler dies, so 10, 15 years time, then at that point your system will have been designed, and so that will reduce the costs drastically. But it is the retrofit costs. You know, we're talking in terms of the heat pump itself. You know, the heat pump installation might be £5 or £6 grand, but by the time you've had to add a cylinder, If there is an existing cylinder, that's almost certainly going to have to change because the heat pump needs quite a large coil. It needs a large volume coil. Because of the low temperature, we have to increase the volume size, so it has to be a cylinder which is designed to run on a heat pump. And there's a few other issues from the control point of view, but that is definitely a problem. Not being able to just retrofit, take one out. However, there is an option which isn't widely being spoken about at the moment because the government isn't going to support it with the fund. There is an appliance which is hybrid. So all of the manufacturers will make a hybrid appliance. So what that essentially is a heat pump with a gas supply. So what it means is the heat pump will do 2/3 of the heat load, but the gas supply will just kick in, top that heat up. Now, because the government scheme, the bus scheme, isn't supporting them, we're not really talking about them. We touch on them in slides, but you'll find in Europe, they're becoming very popular. What it means essentially is you can take your existing boiler out, put a hybrid in, and you've got the best of both worlds. Very similar to the way the car market's gone. People who aren't that confident to go out and buy an electric car straight away have said, well, why don't I get a hybrid? Because I've still got my diesel engine, so I haven't got to worry about running out of diesel. I haven't got to worry about running out of charge. And I've also got my hybrid as well, so I'm doing my bit for the planet. So the hybrid is a really good option. And that is when we talk to customers, we are having that conversation because it may well be that the house, really changing the radiators would be such a problem that can be an issue. But yeah, system design. You're going to find that there would be more and more system design coming into your courses. We sort of slacked it off a little bit with the level 3s, but that will be coming back big time because system design, hydraulic design, pump and pipe sizing now, super critical for these systems to work. You haven't got the luxury of having all that spare capacity that you had with the gas boiler. The heat pump, if you oversize it, won't run efficiently because it will never get up to that sweet spot where it's running nicely. And if you undersize it, it will just be on 24 hours a day trying to chase the heat. So you can't just shove a big heat pump in and go, yeah, that'll be fine. You have to do the design and the calculations. So those of you who are on level 3 programs, those of you who are moving into those sorts of areas, you're going to find that your level 3 programs will have more and more system design coming in because you're going to have to be able to do those calculations to fit.
And also, do you have to change all the radiators in the house to fit a heat pump?
Depending on the size. As a general rule, yes, because as a general rule, those radiators will have been sized to the house. Not always. So if you do some study, if it isn't part of your course, there's a lot of online resources for heat lossing and for sizing radiators. So you can retro calculate the output from that radiator. So it may well be, some of the really old systems, they literally just went big room, big rad. And it may well be that radiator is big enough. You've got a few other issues. You won't get them to run on a microbore system, those really thin pipes, 15 mil sort of minimum really, and those sorts of issues. So there's a little bit on there about the pipe size as well and the pump. But yeah, it is the one thing I think that's causing us the main problems is the cost because of redoing the radiators. And of course, that's a lot about people as well. Whereas they know if they get a new combi, they can pop that on the wall, no upheaval to the house, and the whole system works exactly the same as it did. So there's going to be a lag, but at some point, the gas boilers will be disappearing.
Another question. So, is a flow rate? Hold on, let me just. So, if a flow rate is 55 degrees. And we're going to use a cylinder, how do we get the 65 degrees needed for stored water?
Yeah.
Ooh.
So this again is a problem. What you'll find, a lot of manufacturers are coming at it from different ways. So Daikin's sort of preferred solution is to have an immersion heater, and that immersion heater then is controlled by the main controller. So the main heat pump controller will have a setting in it. You go into the settings, you set your Legionella protection. So the question is based on if the water's only getting up to 55, Legionella temperatures are between 20 and 40. So the temperatures at which Legionella really likes to grow are anything above 20 and anything below 40. So we need to get we will normally try and get that 65 temperature, hit that, and what the manufacturers will recommend is that you have an immersion top up, which will just kick in. And like I say, Daikin's answer within their controller is you go through and you set that up, whether you want it once a week, twice a week, whatever. But the recommendation is to be, you need to hit that once a week. So it just kicks that temperature up, takes it out of the Legionella band. And that is, it's another issue. I think that's going to resolve itself, because I can't help feeling that this is the early days of this technology. You know, you're going to be farther down your career. I can just visualize, you know, a lot of you in 20 or 30 years time going, do you remember that old bloke waffling on about the heat pump and it looked like a dirty grate, and you'll be fitting this tiny little unit that does the whole house. So this is the first version of this kit. It's going to be refined, and it's the big idea happens. When the big idea happens, then the industry shifts. After that, they refine it and refine it and refine it. I've seen it with gas boilers. You know, the first boilers I fitted, you could run them off a plug. There was hardly any control in there. And then they became more and more sophisticated, more and more efficient. You're going to see the same with heat pumps. So they will get smaller, they'll get more efficient. And the minute somebody can crack that 65, 70 degree output from a heat pump, they're going to flood the market. They'll be way ahead. Yeah, that is a bit of a sort of holy grail that everybody will be chasing at the moment.
Yeah, that's it. That's it.
Okay. Any other questions? No? Everybody happy with that? Okay. Right. So we've got this idea then. So our future energy supply. We know that we want energy efficient appliances. We know we want to use the solar and the wind. So these are the ones that we're really going to develop. We're trying to move away from burning anything. And you know, I've given you a little taster there with the wind power. We know that we can generate enough electricity to run towns. We're getting higher and higher percentage of that coming through now. And so that's pretty much working out as we wanted it. The other main energy source that I want to talk about is the solar thermal. So solar thermal, Liz, could you see that? Could you move the whiteboard and the thing, and I'll turn around over there. That's solar thermal on the wall now. So solar thermal is the other idea. It's been around for a while, but we're starting to develop that quite a lot. Essentially what we do, I'm going to make you all dizzy now because I'm going to get her to move the screen. As you can see, all carefully placed.
I'm following round.
Oh, it's going to follow me. Oh, that's great.
Following. Like through the keyhole.
So I've probably disappeared from the screen completely.
Is that? Can everyone see that?
Right. So solar thermal. I don't know if the lighting's not brilliant in this corner. Does that work? Can you see it? Yeah. So this is our next. You know, this has been around for a while. We thought it was probably going to start to disappear, but actually it's hanging on there. The option is with renewable what we're after. We want to use solar energy, we want to use wind. So this is at its most basic. It's such a simple idea. We have tubes on the roof, or we have a flat panel. They absorb the sunlight. We've got a liquid in them. We run it through a pump station, and that heats up the water. Now, if you go online, you can find a place called HeatGeek. There are some sites called HeatGeek, and they're looking at renewable energy and playing about with it in their offices, and really interesting stuff. But they're actually using their solar thermal now to do as a preheat for their heating system. So again, free energy from the sun. They're getting free energy, using it as a preheat to get their hot water system, feeding it into that. Essentially, we literally have a sensor. This is a standard hot water cylinder. The only thing is that for solar thermal, you need a separate coil. So again, because of Legionella, you're normally going to look for another heat source. So you'll either have an immersion or you'll have a boiler. But what we're going to have here is a second coil, and that coil contains the water which is going up into the roof, up onto the roof to heat the water. So again, very, very simple, nice and straightforward. We've got a sensor in the cylinder. We've got a sensor in the solar panel. When this is hotter than that, so when the water on the roof is hotter than the water in the cylinder, we'll turn the pump on, the pump will run, and basically the water will pump up on the roof, down into the cylinder. So again, really energy efficient. All we're running is a pump and a programmer. We've got two main types of collector. You may have seen these ones. So these are what we call evacuated tubes. And then this one is just a flat panel. We use, as you can imagine, we use super insulated pipework. You do need to fill it independently. So we will have a separate fill system for this. And with these, because they're going up onto the roof, we will add antifreeze. So we're going to pop antifreeze into there, and we're going to look for about 20%. So we're going to, one of the ways we're going to get the antifreeze into that pipework there. During the winter, obviously that up on the roof is going to be extremely cold, so we do need the antifreeze for that. We've got the opposite problem in the summer. The temperatures on the roof can go up into the 200 degrees, so it can be extremely hot in the summer. And that's where we have to be a little bit careful with the design. So you don't just want to go putting 10 of these panels on your roof, because that would be redundant heat. But it's why we're starting to look at other uses for the heat. I think probably the best, you will find up all of the countries where they've got a lot of guaranteed sunshine. As you drive about and go to Australia or go to Indonesia or any of those, you're just going to see them on the roofs all over the place because it's free hot water. So very straightforward solar thermal. Few issues about stagnation and things like that, but other than that, nothing really complicated at all. So what do you think about solar thermal? We've got any questions on that? You have
4 minutes left. No more questions. Well, there we go.
Okay.
Any more questions, anyone, for the last few minutes?
Okay. I'm going to wrap it up. Thanks ever so much for listening to me. I've really enjoyed talking to you. I hope you've heard something that you hadn't heard before. I want to encourage you because it's easy for me. I'm looking at a career for the other. You look up, so I'm looking back on one, and you're just looking to start off. This we're going to see some fantastic appliances come out, and you're going to see whole technologies come out that we won't even have taught you about because we'll be catching up trying to teach. The things that are going on site at the moment are really exciting, and you are part of that journey. You're part of that process. That you're going to be specifying, you're going to be buying the kit, you're going to be advising your customers on what they should do. And one of the things I love about it right at this moment is you go to a customer's house, you're talking about designing their system, and you can actually say, we could do this, we can use that, we can bring this in, we can mix and match these components, you can still have your gas supply, you can do a ground source heat pump, air source heat pump, all of those options. Or, stick to a really efficient gas boiler. You've still got those options. And hydrogen, we haven't even touched on. Hydrogen are definitely here to stay and is definitely going to be developed. Big question over how that works out, but definitely going to happen. So thanks very much for the opportunity to speak to you. I hope you got something out of it.
So
Okay.
thank you everybody for joining. I think the webinar's the internet's going a bit funny. This webinar will be recorded and will be stored on the Green Skills website, which is LocalLondonGreenJobs&SkillsPartnership. And there will be available resources as well for the tutors, and I will send that through. We ask that all students complete a short quiz, and I'm going to pop that over to the tutors now so that you can get your students to complete it. So I hope you enjoyed today. And the next webinar will be on the 6th of December and will be about BIM, Building Information Modelling. So you may be involved in that, you may not, but the next webinar will be on the 6th of December and I'll send more details out. Okay, thank you.
Thank you.
Thank you. Bye.
Bye-bye.
Thanks a lot.